a lot, I guess essentially we're still introducing the topic of AI in medicine. And so this one's a little bit more on the practical tools, right, for the application. That's what we're going to talk about today. And we're not moving. Is this, it's off. Okay, sorry. And, a little, there we go. Perfect. And not yet. There we go. Haha. Okay, so this is just a review. Store, compute, learn. Don't forget that one. Okay, it's just an easy one to remember. And we're not moving. Is there a battery thing going on here? Yeah. Okay, so we touched on this a little bit this morning, and that is, how do you perceive artificial intelligence? So there's two big pillars, I guess you might want to call it, for artificial intelligence. One is called general AI, and the other is called narrow AI. So the easy way to remember this is general AI is everything you see in the movies or on Facebook or Instagram. So it has to deal with, does AI have a consciousness? Does it have emotions? Does it have intuition, creativity, abstract concepts, reasoning? Is it an entity? That is general AI. And that, to date, doesn't exist. We can debate it. Happy to debate it with you. But that would be for another course. But it doesn't exist. We don't have general AI. Are there many groups in the world working on general AI? Yes, absolutely. Many, many groups are. And they may actually believe they're very close to it. But in reality, where we operate is in narrow AI, very focused. Very focused AI, okay? And so that, what comes under narrow AI is natural language processing, of course. Rule-based expert systems, so we touched on that a little bit today, this morning. Computer vision, that's what I do. And what we call specific repetitive functions, so very mundane repetitive tasks that can be taken on by AI, is actually a really cool area. So a lot of you here, so who here would have thought, or still would like to do that? Who would like to apply their knowledge in AI or machine learning to automate logistics in trucking companies? Who's thought of doing that? Has anyone here thought, with all their engineering experience and degree, that they're going to develop a software system to better manage a trucking business? Anybody thought of that? It's actually a perfect application of AI. Because for a company that runs trucks and freight and shipping, it's actually quite complex to know where the truck should be, when they should be there, how much are the loads, what roads are they on, where are the road closures, where are delays, right? So AI is actually perfect for that. So very often in medicine, everyone would just poo-poo that. They'll just say, why would I do that? But actually, scheduling physicians in an emerge department is the same idea. How do we know how many emergency physicians we need on staff at a given time? So if you do a very crude analysis, you're going to say, well, we can only afford so many physicians, so that's an easy one, right? But as you all know, depending on the day, the month, the year, you will have more or less accidents. So I don't know about India, because this is my first trip. But in Toronto, every weekend is when we get more head injuries, because more people are traveling by car, motorcycle, and there are more accidents that lead to head injuries. There's also more fights in bars that lead to head injuries. There are more people that drink too much and they fall and they hit their head on the weekend. So we need to schedule more physicians on the weekend. But have you thought we could just say, okay, well, we're going to have 2 more physicians on the weekend. Easy, done, right? But have you thought that maybe when it's raining, you get more car accidents and therefore more head injuries? So how are you going to predict the rain this weekend? So that's when AI comes in, because it will predict the weather for this weekend and take into account what month it is, and take into account, is there a holiday that weekend, and take into account which hospital it is in the Toronto area, etc., to predict and tell the hospital how many physicians should be on staff that night. That's AI. And so that's not sexy, is it? That's not sexy, right? But it's actually very impactful. So the use cases in healthcare, which we've just talked about, what you guys would naturally think of course, is virtual assistants and chatbots, because that sounds sexy, right? To do that is sexy. And I'm not saying it's not. It is. It's great. It's great. If you can do that, it's great. Remote patient assistance, of course. Fantastic, right? So rural areas that don't have the physicians or the healthcare professionals that are needed could be assisted by AI. Medical diagnosis, of course, right? That's the first thing you think of is medical diagnosis. Treatments, yes, can you assist? Personalized treatment. So we talked a little bit about that this morning. The Vice Chancellor, the president of your university, very rightly so, pointed towards what he called homogenization, right? So meaning everybody has access to the same. But he also pointed out that everybody is different, right? And so treatments are exactly that. So what started to be personalized medicine, I can't remember who said they were in genomics here. Someone introduced themselves and said they're in genomics. Anyway, they're doing genomics research. So genomics, when it first came out, was personalized medicine, was in the drug industry, right? So personalized medicine meant, is the drug that I'm giving you going to work well for you? So that was personalized medicine. But then with the advent of digital biomarkers, we now move into the world of what's called precision medicine. So personalized medicine was transformed into precision medicine with digital biomarkers and AI. Okay? Data processing, patient data processing, boring. There's another example of boring application of AI, but very impactful. Very impactful. Medical image analysis, that's what I do. Fantastic, right? Very sexy, it's great, I love it. And it is impactful most of the time. EHR systems, electronic health records, once again, not sexy, very impactful. Drug discovery and research. That's where most of the money is being spent here. Why is that? Drug discovery and research. Why is most of the money being spent there? Anybody? For trials. But why is there so much attention to that? Yeah, to find biomarkers, but why is there so much attention on it? Why are we not spending more money on treatments or on medical diagnosis? Why are you spending so much money on drug discovery, which is actually using quantum computers? Okay, because of the immense amount of data that has to be processed. It's been a computer, many of the companies are looking into using quantum computers. So the reason that there's so much attention to it is because the pharma companies. You make money. You make money. You spend money to make money. So you're spending money on research in this area to make money with new drugs. So I'm not saying I work with, I already disclosed, I work very closely with drug companies. So I'm not saying I'm a purist and, no, I'm not. But you don't necessarily, need to spend all your time in drug discovery research. You should pay attention to where AI is going to be immediately impactful, which is in some of these repetitive tasks, okay? That's where you can provide healthcare in a cost-effective manner to your population, okay? So all of them are important, don't get me wrong. I participate in most of those. So there's nothing wrong with any of them. I'm just trying to draw your attention to some low-hanging fruit that might be useful. So this is just to emphasize the fact of where we're at. So the FDA, which is the regulatory body in the United States, which is probably the most followed, impactful regulatory body in the world. And why is that? Because of the market, right? Because the American market is just where the money is, right? So where are, as of late, so January 2025, so it's a little out of date, there are 1,000 AI models that have been approved, okay? If you look at the vast majority, you can't see this number because it's too small, and don't worry about it. So the largest piece of the pie, which is about 76% of 1,000, are in radiology, in my world, medical imaging. So why do you think that is? Because it's more important? Why is the majority of all AI approved models for medicine, for healthcare, why are they in radiology? Why do you think? In this case, nope. Because of the data. Because of the data. As you know, artificial intelligence machine learning requires a lot of data for training. Where is most of the data currently in medicine? Imaging. There's just so many X-rays, CTs, MRIs, ultrasounds, PET, right? There's just so much of it that it's the immediate target for AI companies, right? It was actually Jeffrey Hinton. It wasn't very kind. His comment was actually a little hurtful, but he stated that all radiologists were going to be obsolete in 5 years. Those 5 years have come and gone since he made that statement. And it's the opposite. We need even more radiologists. And he actually retracted his statement, by the way, to be fair. He retracted his statement because he realized, oops, that was, probably not the right thing to say. But it is true that the idea that you can replace a radiologist was what drove the industry a little bit, right? Because we have so much data, and then, oh my God, reading X-rays is so easy. What does a radiologist do, right? It's so easy what they do, right? Well, it turns out it's not. It's actually, the human brain is actually really good at identifying, patterns. It's really good at it. And so we found out that it's actually quite tricky to do it using AI. But because of that, the focus was on radiology. Then you have other subspecialties. You have neurology, which is a fairly large, chunk. Cardiology, that's growing, right? So cardiology. Now, interestingly, I don't know if you know, and I'm pretty sure in India it's the same way. Cardiology, the scanning, when you go for scans for cardiology for your heart, doesn't come under radiology. It does not come under medical imaging. Cardiologists are trained to read their own scans. So this piece here, cardiology, a large chunk of that is going to be for reading cardiology scans, right? So heart echoes, right? So it's kind of interesting that it probably overlaps quite a bit with radiology at this stage, right? Okay. That was just a little aside. Okay, so I bring this one up. You can't read this again, I'll tell you. Like, you're all staring at, like, what? I mean, this is a particularly small screen. But what this shows here is by country, all right, what is the interest, the public sentiment for artificial intelligence? This was a survey that was done, okay? So from here, this is the percentage of people who agree that, the question, do products and services using AI have more benefits than drawbacks? So meaning it's a good thing, AI is a good thing. So you can see here, the most interested country is China, which China is a powerhouse in AI. Probably the leader in AI currently, debatable with North America. But it's like almost 80% of the population says, yeah, man, AI is a good thing. So where's India? Third, right there. You guys dig AI too. You think it's great. Where's Canada, where I'm from? Second to last. France is last. The United States is almost last. Germany is just above it. UK is right here. Belgium is right here. Sweden is here. Japan is a little bit better. Right? Do you see a trend? Why are we so not interested in AI? And China and India is very interested in Saudi Arabia. Why is that? More publishing? More data? So why is but this is not asking you. It's asking the general population. And the general population in India thinks AI is a good thing. Why is that? When in Canada, it's like, what is it? A third. About 1 in 3. Why is that? Why are we so negative about AI? Because we don't need it. We are privileged. All of these countries are privileged countries. We don't need AI. We can live happily without AI. That is where AI is going to be useful and helpful in global health. Because the countries who need the help, are going to benefit from it. We won't, because we don't have a problem for radiologists. If I have a prostate exam, an MRI, it's read within a week. It's read within like 3 to 5 days. But I don't know how long it takes in India. First of all, you have to be able to get an MRI for your prostate. Not everybody does. But if you did, how long do you have to wait for a radiologist to read it? I bet you it's not 3 to 5 days. How long? Half a day. And that's a radiologist that reads it. But that's private. That's not public. Totally can't be. Not possible. So that's the difference. Right? In Costa Rica, in the public system, so you're right, private's the same day. Because you're paying lots of money for that. In the public system, you're looking at, like for mammography, you're looking at a minimum 6 months for it to be read, up to 1.5 years. We were just talking about this at lunch. If you have a lump in your breast and you go for a mammography, you're going to have to wait 6 months to 1.5 years to find out if that lump is cancerous or not. And once you do, then you go for another test. So you could be waiting easily a year, at least 1 year, 1.5 years, to get confirmation that your lump was cancerous or not. By that time that happens, if you do have cancer, you've progressed from like stage 2 to stage 3 cancer or stage 4 cancer. You may even die in that period of time. That's a huge problem. It's not a problem for us. That will never happen in Canada. There's no way you're going to be waiting a year for a mammography to be read. You're waiting a week. If you're in the private system, you're not waiting anywhere. But that means you're privileged. So if you're in the private system, you're down here, right? But if you're in the public system, you're up here. And that's the reason perception is different. And that's why it's important to keep that in mind for your research. So here's an example. As I said, I work in Costa Rica, and I work with indigenous populations. So I love showing this picture because I'm sitting here with my colleague in the position, with members of the indigenous community in the area, southern portion of Costa Rica near Panama. And it took us 2 hours to walk to that community, right? And the reason I like showing it is because if you work in my world of data, you never leave your office. It's all computer work, right? So global health has opened that door for me that I have to go and talk to these communities in order to understand their needs and how my research can help them. If I don't involve them, I'm not going to put out any product that's going to be useful for them, and they're never going to want to use it, right? Because they were not involved in my research. So just keep that in mind when you do your work. You need to involve the user, right? You have to involve who's going to actually benefit from your research. Okay, so let's just talk. So I talk a lot about radiology. So today, this talk is going to be a little bit more general. We're going to talk a little bit more about where AI can be applied, not only in radiology, right? So, essentially what we're trying to do is, we're moving, down to a more specific area, which is deep learning, as you know, because that's where most of the research is going. But the AI revolution, let's talk about biomedicine, right? So it's a little broader now. Because that might be useful for you guys. You may not be, able to do projects clinically linked projects, right? You may not have access to clinical care to do your research. But what you might have access to, and a few people already mentioned it to me, is like pathology, for instance, right? That's another area. So these AI tools can be applied to a whole bunch of other different things, right? And you can have, biomedicals, right? So that's going to be mostly in treatment, of course, but diagnostic efficiencies, efficiencies, precise and personalized medical treatment. All of this stuff is going to be impacted by AI. So that's biomedicals, right? And then here, very small, the biomedical applications of artificial intelligence. I'm not going to go through all of these because we'd be here all afternoon. But this is just an example of all of the applications that AI can be used in this area, right? So once again, I'm not going to go into the detail of it, but it's just to show you that there's almost no limit to where you can apply AI. Okay. The key technologies. So it's interesting. This is definitely starting to grow, but the traditional machine learning algorithms, I'm not going to say they're obsolete. They're not. They're still used, a fair amount. But inevitably, the ability to learn with these algorithms, so SVMs and random forest, you're not going to get very far with them, right? So where are we going? We're going into deep learning. So CNN transformers is definitely where we're at now, right? So neural networks. And the reason for that is because you get better efficiencies, better accuracy, but you require so much more data. Whereas if you do the classic machine learning algos, you don't need as much data, but then you're limited. There's a ceiling to your accuracy, to your performance, okay? So that's the reason. And what's next on our, in our world is going to be the foundation models, right? The GPTs, the CLIPs. That's where we are now headed. We're actually not even headed, we're there, okay? Foundational models are a reality. And that's where most of the focus is now, is on foundational models. But who has access to foundational models? Well, unless they're public, unless they're made public, you're not going to have access to it. But there'll be a bit both. There'll always be foundational models that won't be available to you, but there'll also be foundational models that will be available to you. Okay. The obvious medical image analysis with AI is, what can you do with it? So and we're going to talk about that this week. This is just kind of like a teaser. So a lot of it is going to be image analysis, so image acquisition and reconstruction, right? So can we denoise, can we improve images so that whoever's reading the images, improves their ability to do their job, okay? So that's image acquisition, reconstruction. A lot of segmentation. So segmentation means delineating the area of interest, right? Your region of interest, your ROI. That's segmentation. That's a qualitative tool and a quantitative tool. So you can either just identify, the area, but you can also quantitatively provide like how big it is and how much, let's say in two-dimensional or three-dimensional space, how much does that, tumor represent? So that's segmentation. Classification is of course yes, no. So disease yes, no, for instance, right? You can have multiple levels of classification. Locations for hemorrhage in the brain, for instance. And then prediction. So prognosis prediction is tricky. And that one is due to a bunch of things. One is just the algorithms are a little trickier to work with. But another one is we don't have the data. It's just not readily available yet, right? So prognosis, you need change over time, right? You need to be able to predict how you are going to be in a year from now, 2 years from now, 5 years from now. So let's say for cancer, are you going to be cancer-free in 5 years from now? That's what everybody asks, right? Everyone asks, if you're diagnosed with cancer, the first thing you want to know is, how am I going to be in a year from now, or in 2 years, or 5 years from now, right? So it'd be nice if you could have an algorithm that, based on your presentation, would be able to predict where you're going to be in 5 years from now, right? Everybody would love that. So prognosis is very important. I'm going to talk to you guys this week about prognosis in traumatic brain injury. And so that's another question that everybody has. Who here has had a concussion? Anybody? Really? Wow. Okay. Very uncommon. So nobody's hit their head here? Fallen off their bike? Wow. Okay. Good for you guys. But, hitting your head's a bad thing, right? You don't want to hit your head. It's a bad thing. But if you do hit your head and you suffer a traumatic brain injury, you're going to want to know, am I going to be good in the future? So prognosis is very important. And so to be able to train an algorithm to do that is complex, but it would be rewarding, right? To be able to tell your patient, based on your presentation, you're going to be good, right? Or actually, sadly, which is very important to know, for what's called severe traumatic brain injury, is you actually want to know that the patient is not going to recover. Because what you don't want to do is treat a patient who has severe traumatic brain injury in hopes of furthering, keeping them alive when their outlook is just dismal, right? So that's a decision that has to be made with the family, what to do. And so prognosis would help in that respect. So meaning that if prognosis is extremely poor for success, then sometimes you're not going to treat, right? Because your family member who suffered the severe traumatic brain injury, you don't want to put them through weeks of treatment, surgery, if ultimately they're not going to survive. So it's a very difficult decision to be made. But you haven't suffered. Good for you. You haven't suffered a traumatic brain injury. But if you talk to families who have had a traumatic brain injury, it's a big problem to make that decision, right? What to do, right? So it would be really nice to have at least something that's giving you an idea of how they're going to recover for sure. They might recover. They'll whatever, or they won't recover. So this is here's just an example. Actually, my postdoc Ernest is probably going to talk about this, and that's brain tumor segmentation. And there'll also be a talk on radiotherapy. So radiotherapy, inevitably what you have to go through when you have a tumor is you need to shrink the tumor. You need to get rid of the tumor, right? You have to, either you can excise it through surgery or you can shrink it through radiotherapy. So inevitably, has anybody here had a brain tumor? Okay, now I'm not surprised, right? But if you have a brain tumor and you have to get, or any tumor, and you have to get radiotherapy, radiation therapy, right? Right, to get rid of the tumor. What you don't want to do is zap the rest of your brain, right? That'd be bad, right? Because that's bad to, expose your brain tissue to radiation is bad. Right? You want to get rid of the tumor, but you don't want to hurt the rest of your brain. So determining where the tumor is, is very important. And the margins, what's called the margins, is extremely important. And unfortunately, just like everything we've talked about, when you do segmentation, the error in segmentation, just like in classification, there's error, I have the disease, I don't have the disease. The error in segmentation means that when you segment the area, the tumor, you make a mistake. And if you make a mistake, then you're going to expose a healthy area of your brain to radiation. That's bad. Okay? So there's something that you can work on using, for instance, UNets or the UNN UNets in order to do that. Right? So as an engineer, that's fun, that's sexy. Is, how do I develop a model to best delineate, segment the brain tumor? Okay. What else can AI be used for? Genomics. Genetics. So this one is, most of it is what's called gene expression. So I'm not going to go into genomics and genes, but for you, most of you are engineering background, correct? So you're not, is there a biological background? You guys say biology? No? Yeah, no? Okay, so I'll keep it very high level. So your DNA encodes how you create the proteins required for your body to build itself, right? But everybody expresses their genes differently. And in response to your environment or disease, for instance. And so AI can help us study how certain genes are expressed in your body. And if you have variants of genes that lead to inappropriate expression or creation of products that aren't supposed to happen, that can lead to cancers and problems. So by studying gene expression and modeling it, we can address some diseases, okay? So that's called genetics and genomics. The omics, in multi-omics, is when you bring together different areas of medicine into one multidisciplinary pool of information in order to make a decision to predict, to treat, okay? So this is a huge area in AI as well, because you can imagine your DNA is very complex, and the problems are very complex. So meaning when you have genetic variation, so in your DNA, those changes are very small, and you have multiple changes that can lead to the same phenotype in a population. So in order to model that, it's very difficult to do, and AI is perfect for that, because AI can deal with very complex problems. So there's a huge interest in exactly this, okay? In applying AI to this area of genomics and multi-omics. Yeah? Here's another one that, for chemists, who's in chemistry again? There's people here who are chemists. I keep asking who that was. Either people are really shy, and I go, oh, I gotta put my hand up, or completely. What is everybody here like just an engineer or something? Come on, man. Okay, so you know, mass spectrometry, spectroscopy, metabolomics, you know, metabol, okay, for profiling, is another area that maybe you wouldn't have thought of, right? So if you are a chemist, if you are into, you know, the study of materials in that sense, this is interesting too because spectroscopy, mass spectroscopy is all signal processing, right? And signal processing is a perfect target for AI, all right? Because it's very complex, right? And it's funny, we were just talking at dinner about, you know, the idea of frequency versus spatial representation. So here's an example that, you know, signal processing tends to fall into the frequency domain of processing. And so this is, once again, this is all fantastic stuff to help us, like for instance this one, you know, tissue collection, you treat your sample, you get some analysis, and then you do analysis on it, you do spectroscopy or mass spectroscopy, and then the problem, of course, is how do I analyze these results? And very often there's a lot of noise. There's a lot of noise, right? And how do you deal with the noise? How do you get the signal from all the noise? So that's where your AI can help. Your machine learning can help in that. Okay, and so there's a lot of focus in this area as well. Okay. Okay, back to image analysis. So I really do my best to not be so focused on image analysis, but inevitably that's what I do, right? So I'm always going to come back to image analysis. But you know, there are challenges in image analysis, and this is what I wanted to share with you guys, that it's not easy. And that's a good thing. So I think I said it already this morning. If it was easy, we wouldn't have a job. So don't complain that it's hard. It's a good thing. You want it to be difficult, or everyone would be doing it. So the biggest problem, of course, is you get enough data, enough quality data, right? This one here, for sure, and dealing with data set and algorithm biases, these two, compared to downstream, computational demands, compatibility of systems, legal ethical questions, we're going to cover all of this week. This here represents, so data curation, right? Making sure you have the right, clean data set that's labeled, probably represents about 80% of the work. If you are privileged as an engineer, and what you're waiting for is to receive the data set, and when you get it, you say, oh, I can't work with this. Can you please address the data set and fix it for me? You're very privileged. It's very comparable to a statistician. Statisticians are privileged as well. Because if you ask them to analyze a data set for you, to test a data set for you, they're receiving a spreadsheet with all the data fixed for them in the format they want it, correct? And then they run the t-test. Ooh, big deal. So it's the same for engineering. You're going to receive a data set of images that are correctly labeled. Everything is pristine, perfect. And then they ask you to create a CNN binary classifier, disease, yes, no. Who cares? Like, that's easy. Come on, man. That's 20% of the work. That's the fun part. Modeling is the fun part. The hard part is getting the data in the format you need it, with the quality you need it, and the correct labeling. And that involves working with your user, right? Working with the people that know the data, that produce the data, that use the data. That's the hard part of everything we do. But it's actually a crucial part, especially when you deal with bias. Okay? So we're going to talk about biases in training, and they happen all the time. I'll show you that I can tell the difference in sex from a knee ultrasound. So I'll show you the picture. I don't know if any of you have had an ultrasound of there anywhere. Ultrasounds are very difficult to recognize any structure. Very weird, right? Ultrasound is a different, just because of the way it's tomography, what's called tomography, which is slices. But it's difficult to interpret what's going on. But I can tell with over 90% accuracy if that knee belongs to a man or a woman. And there's absolutely no way when you see the images that you'll believe that. But AI can do it. So if I only train, for instance, in hemophilia is what is called a sex-linked disorder because it is primarily in males, okay, because of the recessiveness. Females can have it, but it's extremely rare because of just the math of the recessiveness, but also B, you almost have to make an effort to end up having a baby girl that has hemophilia, okay? Because you'd have to have the male and the female, the mom and the dad have hemophilia, and what responsible parents would actually go ahead and have a child when you both know you have hemophilia? It does happen, but it's quite rare. So if I train all of my data set on hemophilia, who am I training with? What's my data set look like? I'm training on knees. What knees do I have? They're all males, aren't they? Or vast majority are males. Do I care? Who's my algorithm going to be used on? Probably males. So do I care? I should though, and I did. Because, boy, that's not fair on the women that do have hemophilia, because they can't use my algorithm. That's bias. And that's an extreme example. And what happens all the time is where you have a disease that's equally prevalent in males and females. But because of whatever circumstance, the data that was available was mostly male. That happens all the time. Happens all the time. For whatever reason. Could be cultural, could be religion, could be whatever reason, the data is not there for women. So the algorithm is developed and it's put out there, but it works 91% accuracy in males, but if you actually test it, it works like 70% in females. Happens all the time. And that's because of biased data. Okay? So that's the challenges that you need to face and you need to think of because it's a huge problem. Biomarker discovery, patient stratification, all the omics, right? So we already talked about that. Data-driven discovery is a thing now. It used to be a naughty word, right? Data-driven is naughty. Oh, that's data-driven. But now, because we have so much data and we have the ability to work with that much data, it's okay. So data-driven is definitely something that's happening now. And AI contributes to this in a big way, right? So this is where we're looking at unlabeled data. So we were talking this morning about unsupervised learning. Unlabeled data, you get some interpretation algorithms, and you process them, and then you get your outputs. See here, where you're getting clustering. So that's learning. That's the learning aspect of it, okay? And that's huge. So there's an example in omics that we're actually trying to apply unsupervised learning. For researchers, we have tons of tools. So this is just something I wanted to just touch on a little bit. This is just a complex little, pipeline, right? But we all use tools. So the only thing I'm going to stress is that tools are great, absolutely. A lot of modular, we just talking about it at lunch. You drag and drop, you connect stuff, right, to get your algorithm to work. There's definitely more and more and better tools, almost week over week. But be aware, take the time to understand what you're doing. Just, not every day, but at some point in your degree or in your research, just take the time to actually understand what the tool does and what it's doing for you. You don't necessarily have to, do a deep dive into the code, but you should understand what your tool's doing, and the reason for that is because you may find out, oops, some of my assumptions are not quite right. It's not quite what I thought it was doing, and you need to be aware of that, okay? So using the tools is fine, but just dig a little deeper. We are academics here. We're supposed to do that. If you're working for a company and the company's telling you to use these tools only and develop this for me, okay, sure, that's your job. That's fine. But, as academics, understand what you're doing. It will pay off in the end. So here, this is the bench to bedside, and importantly, what's called clinical integration. So this piece here just shows us we need to validate with real-world data. So just try and think, what's next for me? If I'm an engineer and I'm working on an algorithm, what's next? How do I get what I've just developed used in the real world? So you can't get through external validation. That's the first thing you're going to have to think about, right? Then you have regulatory approval. For us in Canada, it's called Health Canada. I don't know what it's called in India. Maybe Health India. I don't know. But there's going to be a regulatory body in India that you're going to have to get your algorithm approved in. Then, once it's approved, then you're going to have to integrate it into clinical workflow. And most importantly, afterwards, you're not done. You're still not done. Once it's been taken up in clinic, you then have to monitor it and make sure it keeps doing what it's supposed to do. So why is that a concern? Does anybody know that? That's called governance, right? So why is that? If your algorithm, you just developed an amazing algorithm, why would it change? Why would it change? Why would you expect the results to change over time? Why? Anybody suggest? Comes down to stats again. What would it be? You guys heard of distribution shift? Data drift? You guys heard of those terms? Both go, okay, sure. Things change over time, and your algorithm may no longer fit the data it's supposed to represent. And that's called a data shift or a data drift. So the distribution of the features that you use to train your algorithm could actually change over time. So here's a good example. In medical imaging, let's say, okay? I am training on a CT scan, doesn't matter what. Chest, let's say chest CT, okay? Looking for lung cancer. All of my data came from 3 sites, right? Lots of data, all fantastic stuff. But as you know, CTs are a form of X-ray, correct? So you're exposed to radiation. Not a good thing. So you want to minimize your dose, how much radiation you're exposed to. So let's say some of my centers have adopted a new CT scanner that specializes in what's called low-dose CT scanning. Okay, so less. When you do low-dose CT scanning, the imaging that you're going to receive is going to be just a little bit different. It's not going to look as crisp and clear. But for the, the radiologist or the internist or the clinician, they're still going to be able to do what they have to do, right? Which is to find nodules in your lungs. The only thing is your algorithm was trained on the previous versions of the CT scanner. So now you have a subtle shift in some of the data, right? In terms of the features in your CT scan. And so that is an example of where your algorithm is going to stop being as performant because the data it's reading is slightly different. There's also other distributions for diseases. Diseases change over time. The way they present changes over time. COVID changes over time, right? So there's an example. So you have to be aware of that. That's why continuous monitoring and updates is so important for your algorithm. And that's a good thing for you guys because it keeps you busy. Keeps you employed as an engineer. It means you're attached and keep working for your algorithm. Where's the next fun stuff? I do a fair amount of this, and this is generative AI in biomedicine. So generative AI is all the fun that came out with GANs, like I don't know how many years ago it was, like quite a few years ago, like GANs made a big splash, right? Generative adversarial networks, right? So they can make, you know, dogs and cats and faces and, you know, they replicate it. But they've now evolved. You have more than GANs now, although GANs is still really big, right? So NVIDIA, with the style GAN, is still used extensively. I still use it a lot. But you now have, autoencoders we'll skip over, but we have diffusion models that are all the rage now. The only thing with diffusion models is they require a lot of data to train. So they're a bit of a limitation that way, but they work extremely well. And what we're trying to do is simulate some of the data that we would need, right, for training. And so by using generative AI, we can either simulate data just for representation. So let's say you're training to be a physician, right? And you want to identify from a scan or from a test or from whatever what the appearance would be for that disease. So you could look up a bank of images that's going to have those diseases. But what's being done now is you can generate it. You can just ask, text to image, right? You ask, I want to see this, give me an image. Then there's no privacy issues. And you can be very specific. You can say, you know, in a male, a female, how old, all that kind of stuff. So that's educational. That's almost educational, right? That's training and education. But in AI modeling, very often we don't have enough data. So you need to augment your data set. And so one way that's being used is using synthetic data. Is it perfect? Absolutely not. It's really not. But is it helpful? Yes. It's not perfect because you can imagine if you replicate exactly the same data, the algorithm is not going to be challenged to learn anything new because it's exactly the same data. So you need to create synthetic data that's different than your data set, okay? And that's very challenging. So it is possible, in my experience, 8-12% increase in accuracy is the best you can hope for. I've never seen anything better than that. So if I introduce synthetic data into my training, 8 to 12% is the best that I've ever had work, okay? So is it perfect? No. Is it helpful when you're working with very rare diseases or something like that? Yes. Or you just have very small data sets? Absolutely, it's helpful. What we'll also talk about is being responsible in what we do. So principles of ethical AI in healthcare. So you can see here, there's a whole bunch of different labels here. PIPEDA is our privacy laws in Canada, okay? But in India, you're going to have exactly the same thing. You have your privacy laws. Your compliance, once again, Health Canada, you're going to have exactly the same thing in India. What's required is there's legislation. I don't even know if India has it yet or already does. It's very possible that India probably may have already in place legislation to govern AI, which you need transparent and fair AI. Canada, we were just about to pass it through the parliament, but then we had a switch in government, and it got paused, but it's going to happen probably within this year. And that is, if you're going to use AI in medicine, you have to disclose and inform the patient. You have to give them the choice of a second opinion, and it has to be explainable. You have to be able to explain your algorithm, how it works, how it made the decision. That's going to be law in Canada. And I suspect if it's not already law in India, it will be as well. So why do we need all that? Well, it's basically to say, you know, it's the social aspect of AI, right? So the impact on society. So social well-being, governance, value alignment, I'll touch on that one in a second. Unfair bias, we've already talked about bias. Privacy and security, no-brainer. Accountability, yeah, who's accountable? That's going to be a question. Human-centered means, once again, we don't want to lose sight of who AI is supposed to be helping us. Reliable and safe, of course, just like any medical device or drug. And transparency and explainability, which I just touched on. The one I want to go back to is value alignment. AI has no concept of value. AI has no concept of morality, ethics. What is ethical? What is moral? What is morally right? Is what is morally right the same here in India as it is in Canada? What do you guys think? You think it's the same? It's probably similar, but it's not the same. Are our values the same in Canada as they are in India? No. And you know why? Because they're two different communities, two different societies. Your country, our country, set our laws to abide to our moral compass. You all have your moral values. We have ours. And they're set by your culture, your religion, your history. That's who sets it. So if I develop an AI algorithm in Canada and I sell it to you in India, how do you know that the algorithm I developed is in line with your values? You don't, do you? That's a problem. Because it is assumed that these values are in line. So meaning that when I develop my algorithm, it applies to anybody in the world. But that's not true. And so in the process of developing your algorithm, you must take into consideration the values for which this algorithm is going to be used for. Because they may not be correct. They may not be, appropriate for the community that is going to be using your algorithm. So remember that, because it's very important that when you collect your data and how you collect it and who uses it and what the biases are in your data are going to be impacted by that. And AI has no clue about value alignment. It does not understand that. You do, but it does not. Okay? So that's very important. Where are we going in the future? We're already there. We're already there. But multimodal learning, for sure. We'll talk about that. Self-supervised learning, already there. Foundational models. Federated training, explainability. Definitely federated training. I was a big believer in it too. Does anybody here know federated training? Yeah, so it's kind of sharing the ability to train on data sets that are not all together, right? That's federated. But you're doing it across institutions, let's say, right? The problem with federated learning, the concept is great, the application is brutal. The actual implementation of it is nasty and very expensive. So it's a real barrier, right? So I don't want to, especially it's being recorded. I'm okay with federated learning. It's just I haven't seen huge success on it unless you're really, really, really rich. You know, if the project has millions and millions of dollars to do what you want to do, then yes, absolutely, you'll be successul. But for what you and I do, federated learning is just the barrier is too high to overcome. Right? It's better to go out of your way to share your data. So I've been more successful at, putting together sharing agreements than I would be to trying to do federated learning where you don't have to share your data, right? You're kind of sharing your data, but you're not actually sharing the data. It's easier to get the lawyers involved and just try and get through privacy, right? And sharing, data transfer agreements. Explainability is huge. We'll talk about that too. The need for explainable or interpretable AI is extremely important. As I said, it's law. So explainable AI means you understand how the model works, the parameters that are in your model, the decisions that the model's making. Interpretable AI is the ability for us humans to interpret the results from your AI. So for example, a heat map that shows you on the image the area that the algorithm used to make the decision is interpretation. Okay? Explainability is going to be in the bowels of your model. You're going to be able to explain how the model came to be the way it is with the parameters it has and the weights it has. Okay? That's the difference between explainable and interpretable. But it is very important, and we can talk about it. Multimodal, if you don't know it, if you're not a hands-on programmer, the ability to merge together, it's actually called fusion, to fuse together disparate data types is really not easy to do. And multimodal modeling is very tricky for exactly that reason. Because you can just do it, but you have no guarantee that you're doing the right thing or it's working correctly. That's the tricky bit. And how you weight the fusing is very tricky, right? And when you weight the fusing is very tricky. So in summary, is this it for us? Yeah, look at that, we're almost done. And you're all still awake. That's fantastic. So in summary, start small, think big, of course. Collaborate widely, really important to collaborate. And be ethical, right? So that's, in a nutshell, that's what you want to try and do. This is the whole personalized medicine, digital therapeutics. This is the nice circle here, right? This is the raw data, genomics, dry, wet lab research. So you guys can start thinking about where am I getting all this data? Each one of these steps, right, leads to data collection and management. And then this is what you guys do down here. Your algorithms, right? And then you can, digital therapeutics, that's something we can talk about too. That's the idea of using your phone, right? So digital therapeutics is like mHealth, where you have it's just another way of calling it, right? So digital therapeutics is actually from the drug industry. Okay, so if you think of what's called software as a medical device, a SAMD, a digital therapeutic is a software that's used in the context of treatment. It's called digital therapeutics. A broader term is mobile health. Okay, so meaning using, mobile health is specific to your phone and mobile. Digital therapeutics can either be phone or it can be on a computer, but it tends to be on the phone. Anyway, just a little bit of a subtlety there. But all of this, what I hope I shared with you today is to just give you the ability to see where you can apply your knowledge. And very often, no matter where you are, it doesn't matter if you're here in India, if you're in any country, very often you're very tunnel vision, right? In terms of, I have access to this data, so that's what I work on. You stop there. Right? Or, I can only think of these rare diseases or these common diseases, And so that's the only thing I'm going to apply my knowledge to. But, you should spend a little time to just think, there's way more in healthcare and biomedical that I could actually spend time on. If you're a signal processor, and that's what you really enjoy, is signal processing, there's just so much you can do in signal processing. So, expand your horizons a little bit and find a new area to apply your knowledge and skills to, and it might be entertaining for you. It might be fun, right? To do something a little bit outside the box, or a little different than what everybody does in your department, let's say. You'll be surprised at how you can use the same skills, the same idea, the same methods, the same everything, but in a completely different area that you would not have thought of. Okay? And that's it for today. Questions?